Welcome back to Organic Chemistry. Today we're going to consider the other part of the equation, the SN2 reactions and E2 reactions. That would be second order reactions, where we had first order reactions last time. So what are we interested in? We're interested in the reaction where two molecules, the starting material and the reagent, interact to form the product. If they're going to do that, we're going to effectively have to add the approaching group, the new thing, the OH in this case, before the chloride has left. Before we were making the chloride or the other group leave first in the SN1 reaction, and then the other one came along. This is effectively exactly the same, so we're going to switch this bond. You can see that we're switching this bond so that we've got a new substituent on it, changing this chloride to an OH, and the two possibilities are we take this off first and then we have carbon with only 3 bonds and it's unhappy, or we add this first and we have carbon with 5 bonds and it's unhappy. We discovered last time that carbon with 3 bonds is only a little bit unhappy. It is possible to hang around. Carbon with 5 bonds is not. We cannot stop the reaction at a 5 bonded state. Carbon won't do that, but it can go through that state. So what we have is this molecule in 3 dimensions. I've drawn the hydrogen on to make it a little bit easier to see all of the groups, and we're going to be looking at how does it form a 5-membered state. So finally we've got there. I've got a bit better sound. Let's hope that it works. Here is what I was trying to show you. We've got our bond between the chloride in this case and the carbon. And we've got our 2 antibonds. So this is our bonding orbital in between. It's formed from an sp3 hybridized orbital from this carbon here, and an s orbital or a p orbital from chlorine. And it forms this bond in between them. But it also forms an antibonding orbital which is on the outside because it's a sigma bond. The antibonding orbital is exactly in line, and it's in between the 3 other bonds. So if we have something that comes along, that would be an OH minus, and it's got extra electrons. I've drawn the electrons in red, the absence of electrons in blue. So we've got our OH minus, and it's got a lone pair of electrons. They can donate into this orbital here. That will weaken the bond by putting electrons into the antibonding orbital. That weakens this bond and causes it to move out, and it puts us into a state in between where we've got 5 bonds temporarily. So I've drawn it out over here. Let's have a look at it. We've got a long bond coming in and one leaving. We've got a bond coming in from the OH minus and a bond leaving from the chloride. Camera's looking up at the sky. It's all going wrong today. So we've got a bond coming in, that's the OH minus. We've got a bond leaving, which is the chloride. They're both longer than the normal bond because they're in an intermediate state where this one's coming in and this one is leaving. And we also see that these 3, the methyl group, the hydrogen, and the ethyl group in this case, are pushed down to a flat state because there's an atom on both sides. We've got a 5-membered transition state, and the 5-membered state is typically trigonal. So we've got 3 trigonal is a pyramid anyway. We've got 3 in a plane, and we've got 1 above and 1 below. As it pushes through, so as this bond shortens and this one breaks, I need a minus on my chloride. if you can even see that, yep. Then it pushes through and we end up with the opposite enantiomer than we had before. So this is where the chirality becomes interesting in organic chemistry, because we started off with one direction, well, not the band, but this particular compound here, and we changed it to the other configuration. Okay, we've changed the substituent. If we then put the chloride on again, it will go back to this one. If we changed it to if we changed it in three ways, so we changed it from chloride to OH to iodide back to chloride, we would have the opposite form. We would end up switching the configuration. Not that that's necessarily possible or in a decent yield, but it is a way of switching the shape of one molecule, switching the image of the molecule to the mirror image, from changing the chirality, because we've moved these three down and we've effectively taken this group and put it on the top. There's a lot to look at here. One of the important things is the difference between what we in chemistry call an intermediate and what we call a transition state. So an intermediate is a chemical that exists, that can stop at. So if we have an energy profile of a reaction, I've got any board that you can see over here, that's good. So if we have a reaction that goes through a hump, this would be the activated transition state here. This would be an intermediate where we can stop. If we cool it down enough, we could stop and catch this chemical, and we get to the end point. On the top of these things is what is called a transition state, and that is where we have a chemical like this, which it can't stop at. It's the top of the energy profile. It's the highest energy point, where we've got 5 things connected to carbon. So it pushes through, and it's going to fall in one direction or the other, whatever we do. We can't balance it there. It must go through it. We can surmise that it must go through it, but we can't catch it doing it because it never stops there. Whereas the transition state, depending on temperature and depending on the reaction, we can catch it in this state. So we can freeze it into the state, or we can measure it in our reaction mixture if we know what it looks like. So we can take our carbocation, for example, calculate what spectroscopy it should have, and measure it in the reaction mixture. So that tells us everything we need to know about SN2, but obviously there's a lot hidden in there, that we flip the chirality from one side to the other, although it depends what we add on, obviously, because we might change the order of the groups, but we flip where the other groups are organized when we do the reaction. If we want to do it, and we want to retain the chirality in this form, then we'll have to do 2. If we are looking at the mechanism, we can see that we're attacking into the anti-bonding state of the bond, which is logically making this straight line bond all the way through, because the anti-bonding state of single bonds are directly behind. The anti-bonding states of double bonds are out on the sides, because obviously the double bonds are on the top and below, and the anti-bonds are also on the top and below. That was what we had in our carbocation state. Effectively, we're going into an sp3, from an sp3 to an sp2 state. In this case, we are staying in the sp3 state, but we're going into the anti-bond, and this one is, the electrons effectively are switching over from one to the other. The other important, in an E2 elimination, just like in an E1 elimination, we will have a base come along, and the base is going to steal a proton, and the proton will leave, and then also the same leaving group that the Cl- will leave as well. In the SN1 reaction, we had the leaving group leave with its electrons, leaving a positive carbocation, and then the base took a neighbouring hydrogen, not this one, took a neighbouring hydrogen, either these or these. In an E2 reaction, it's going to be at the same time because it's second order, so we need our base to come along and take one of these protons. Because these are the same, I've made the molecule simple to start with, we're going to take away this side, but just because I've drawn those out. The geometry is the same, so we would have a double bond that is trying to form. That's this line here. That will be the double bond that's trying to form. And so that will be an orbital on this side and an orbital on this side, coming from this orbital here, which has its antibonding orbital in the back, and this orbital here on this hydrogen also having its antibonding orbital in the back. So that's the one that's going to make the double bond. So we can go back from there and say it must be this hydrogen here, which is pointing in the opposite away from the chloride. These hydrogens obviously could react, but they'd have to rotate round to this position. If there was something stopping them rotating, it would always be this one here that is flat in the plane, because then our double bond can form. Remembering that double bonds tend to flatten the molecule. We need an electron density on this side of the single bond, and we need electron density on this side of the single bond, and that's going to come from here, and it's going to come from here. So those are going to go in, or in this case, we're going to take a base. The base is going to donate electrons into the hydrogen. This bond from the hydrogen to the carbon is going to go into here, and this is going to kick out and knock our chloride out. So these two electrons are the ones that become the double bond. It is these two orbitals that do all the work. What that tells us is that in more complicated molecules, we can guess which hydrogen is going to react, because it must have this configuration where they are opposite. We like to call it in organic chemistry something really complicated called anti-periplanar. Anti meaning they're on the opposite side. Syn would be on the same side. So this hydrogen is syn to this chloride. This hydrogen is anti to this chloride. But in simple terms, it's the one that is flat and on the opposite side, because we need to have orbitals that will generate this double bond, one on each side of the single bond. So if we take this example with a ring molecule, ring molecules can't rotate because they can't flip completely inside out unless they're very big. Six-membered rings definitely can't flip completely inside out. We're looking for a hydrogen that is anti-periplanar, that is on the opposite side to our leaving group, which is the chloride atom, again in this case. This hydrogen, which is a possibility, can't leave because it's on the same side. It's a syn hydrogen, so it's on the same side, it can't leave. It can't do E2 anyway. This hydrogen on the back here can, and so we will only form one product. In this case, it's hard to tell which product we have because I haven't drawn another bond on there. So I'd have to put a double bond somewhere else or some other substituent on there so that we would know what happened, because it's symmetrical otherwise. But when this leaves and forms a double bond, it's always this one that does the reaction in this case. Because we have formed a double bond, the stereochemistry of this carbon is lost, or the information is lost, it goes flat. So we end up with a not so chiral product, so it's hard to tell. But if we label it in some way, we would always lose this hydrogen. It will always go in this direction because it only had one hydrogen that was in the anti-periplanar configuration that was in the right direction to be lost. Going back to this reaction, we can see, or going back to this reagent, we can see if this does an E2 elimination, there are two possibilities. Either this hydrogen could leave, which is in the anti-periplanar configuration, or this hydrogen can leave. So we would get two products, but what we're interested in, if we're trying to do organic chemistry, is which one are we going to get most of? Because that is going to be our major product, that's going to be what we're trying to make. Just like in SN1, just like in E1 elimination, there is a preference. So in the SN1, when this was lost, the most stable carbocation was formed. So we would tend to form, lose the proton box. Okay, let me try again. I think I messed that up. So if we have this starting material, which is what we drew to start with, we have two hydrogens that could be, or two groups of hydrogens that could be in the correct configuration to leave via this reaction. So our base could come along and take this proton away, or it could take this proton away. Obviously they can rotate, so these two are equivalent, and these three are equivalent. There's no difference between them. But there is a difference between the ones on this carbon and the ones on this carbon, because the two products have different energies. If we look at this product, bang, bang, this product, versus this product, we can see one of them is a primary alkene and the other one is a secondary alkene. And what we know, there's a rule called Science rule that says the more substituted alkene is lower in energy and so will tend to be formed if the mechanism allows it. So we had an example just now of a ring where only some products were allowed, and you can set it up so that it cannot make the more substituted product. But in this case, there is nothing stopping either of them forming, and so we will tend to form mostly the secondary alkene, but we will also form a little bit of the primary alkene. It's always a mixture, or it's very often a mixture. This is obviously not very efficient, but if we want to form the secondary alkene, this E2 elimination will work pretty well, because we will predominantly form the lower energy product. Here we will get it, let's start again. Why is it lower in energy? It's lower in energy for exactly the same reason, that the bond is aligned. We've got this double bond with its orbitals here, and we can donate some electron density, or we can share electron density with one of the hydrogens on the next carbon. Whoops. So we can share that into here to end up with a partial bonding state that enables this double bond to be shared through the molecule. And we had the subject last time that the bigger something is, either an electron cloud, and a charged species, or a radical, the more stable it is, the lower in energy it is, which makes it obviously more likely to form. In this case, we're sharing with the methyl groups on the end. If we had another group on one of these ends, so if we had a forked group here, then that would be even more likely to form. So if we had another carbon on here, this hydrogen would be particularly good at being lost. We can view it, hang on, we'll come back. There is another way to view this. We could say these hydrogens on here, which we can call protons, are more acidic than these hydrogens on here, because these ones, they're exactly the same distance away from the chloride, which is drawing electron density away from this carbon, but these ones are also close to this group here, which is donating electron density into this carbon, which allows it to be more stable if it is if we take this electron away. We have more electron density here. We can take away, oops, that's not working. No, I'm not going to say. So in the manual, in the set of slides, in any organic chemistry textbook that other people might look at, there are a whole set of examples of reactions where more complicated things happen. We will not introduce those right now. We'll go on to those slowly over time, because we first of all have to understand this piece. We'll stop there for today, come back to it another time.